Right, and sort of talking about, the last speaker's talking about manufacturing transistors. I work for this company. We make these big monstrous machines called ion implanters. And you take a wafer that's been masked and etched, and you stuff it in there, and we N on it. And then they take it out, and you mask it and etch it, stuff it in there, and then we P on it. And then they do it again, you get more N's on it. So I get to do C# programming, C++, Verilog, and all kinds of stuff, so it's kind of fun. So that's what I do for work these days anyway. But in my spare time, I try to build computers. And does anyone not know what a PDP-8 is? Because I should start with fundamentals. Okay, there's a PDP-8. They actually have one over here, I noticed, and that was pretty cool. Anyway, so once upon a time, I wanted to make, since I was little, I wanted to make a computer out of vacuum tubes. So I was thinking a few years back, what could I do to practically make a computer? So what kind of computer would I make, okay? And it had to be one that would, sort of minimize the amount of, circuit elements that you would need, the minimum number of gates. And so I thought, okay, well, PDP-8, is a pretty simple computer. It's just 12 bits, right? And it's got just an accumulator and a program counter and a memory address register in it, so that's just 3 registers. And it's got lots of software for it already, right? Your operating systems and all this crazy kind of stuff. So I said, yeah, that should be fairly easy to do, and keep the project constrained, okay? And I also had the desire to make it, okay, I'm just going to do the processor, because doing things like, memory and all, whatever they would do back in the day for things like, storage or memory and that kind of stuff was going to be impractical. So I just limited myself to just doing the processor, okay? And everything else, for memory and storage and whatever is done on a Raspberry Pi, okay? So basically I have the processor, a GPIO connector, which could be thought of as the memory and I/O bus or whatever, and then a Raspberry Pi on the other end. So keeping those constraints on it, I think, made it practical to do, okay? So anyway, like I say here, I call it the PDP-8V for, like I said, vacuum tubes or valves or whatever you want to say. And I have a Hackaday I/O page I just put up maybe a month ago or so. But anyway, I thought about the design, look at the instructions on a PDP-8. I can scroll down here a bit and do that. Well, I don't have the instructions here, but the PDP-8 instructions are very simple. There's just a, add, there isn't even a subtract instruction. There's just add and AND. So that keeps your ALU pretty simple. Keeps the, the gate count down on that. And then, there's a simple jump and jump to subroutine. And that's about it, and an increment and skip if 0. And that's about it, for the instructions. So that's fairly simple to do. Yeah, and there's another instruction to, negate the accumulator, because you have to be able to invert bits and do shifts. So there's a simple instructions to do that. So I thought about it, and I came up with this little block diagram. The ALU is sort of the heart of, selecting things to do, and then the registers are over there, sort of on the middle of the screen there, the memory address register, the program counter. Top there is the accumulator and link register, and link is what they call the carry bit. I don't know why they didn't call it carry bit. They call it the link bit. And then at the bottom is how the Raspberry Pi hooks up, and it just hooks up as, another register. It just looks like a register to the rest of the thing. So the output of the ALU goes to the inputs to all these registers, and then the outputs of the registers go back into the ALU, either into the A or the B input. And the way I worked out whether they go to the A or the B is just, when I came up with the steps, the states that the thing has to go through to decode how, what needs to go to the ALU. And again, it just does the bare minimum that it has to do in order to accomplish these instructions, okay? So that's the basic layout of of how the circuit is put together. All right. Then I had to come up with the steps that this thing goes through. Okay. So the PDP-8 has these three major states called fetch, defer, and execute. And that was convenient to work with, and it fit the way I was going to do things. So I worked out fetch, defer, and execute. Now, one thing, the way I do clocking is it's a fully synchronous design. And you can think of the flip-flops as being, all the flip-flops as being in one vertical column, and they all clock off the same clock, you know, ker-chunk, 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 right? And the outputs from the Q outputs go through a bunch of combinational circuitry and come back around to the D inputs. Okay, and so all that stuff has to flow through all the gates, back around to all the D inputs, and ker-chunk, ready for the next cycle. And that just keeps everything simple, I think, personally. And someone was talking about the 1130 and the asynchronous design, and it's, oh, no. Anyway, I think it's just a lot simpler to do things with synchronous design, you know. And that's the way, like, FPGAs do stuff now, mostly is, you know, just ker-chunk the flip-flops. Every clock cycle, ker-chunk, ker-chunk. Some of the gates, like, I think the ALU has a gated clock, so I can suppress loading the ALU. But the program counter, it was easiest just to make the program counter ker-chunk every cycle. If it doesn't increment, well, it just ker-chunks its old value into it, you know. It's either ker-chunk its old value in or get a value out of the ALU or increment, one or the other. All right? So that's how the design goes. And each one of these steps, fetch 1, fetch 2, each of the defers is just one clock cycle, okay? So one state per clock cycle. And there's a little blinking light on the front panel, on my front panel. Of course, I'll show you at some point for each one of these states so you can look at the LEDs and see what state the thing's in, all right? So this here will detail, like in fetch 1 state, it's taking the program counter and gating it through the ALU, which also, you know, since the output of the ALU goes to the Raspberry Pi can see, okay, what's in the program counter. And then it sends a flag to the Raspberry Pi saying, okay, this is a memory read. We want to do a memory read this cycle. So here's your address. And then it goes on to fetch 2 state next, where the Raspberry Pi data coming back, okay, the Raspberry Pi saw that, oh, the tubes want a memory read last cycle. So coming into fetch 2, it's going to say, take the data from the Raspberry Pi and put that into the instruction register and take the program counter. Now we want to run that and increment the, getting stuck here. So we want to increment the program counter. So the program counter has a little circuit in it where it can increment itself, a separate circuit. So it can increment itself separate from the from what the ALU is doing. And we also want the ALU, because it's a memory reference instruction, we want to get the ALU to generate the address of what the operand is, like what memory location are we adding or are we going to deposit into and stuff like that. So that's all done during the fetch 2 cycle. Okay. Now I think the way the PDP-8s did it is they have one clock cycle for this whole thing, but it was divided into several phases. So they would do this all as one clock cycle, you know, with a big asterisk that the thing is divided into one phase. I just decided, in my mind, it's just simplest just to use, you know, one clock per operation, or one clock in this thing instead of, you know, having like a 3-phase clock or anything like that. I just think it's simpler, so that's the way I did it that way. All right. I don't know if people have interest in me pounding through all these other states, but, you know, defer is very simple. If it was an indirect reference, okay, you know, the tubes send out the address to the Raspberry Pi and say, I want to read that memory location, and then the Raspberry Pi, the next cycle, responds with the contents of the memory, and the tubes clock that into the memory address register. And then the PDP-8 has this thing, auto increment, whereas if you use deferred memory reference through these magic memory locations, you know, 10 through 17 octal, that it will increment that thing before it will increment that memory location before it uses the pointer. Okay, so that's how the defer cycles work. Again, you can step through if you want to look at this on the web. There's the web page address if you want to look. And then here's the exact, like there are up to 3 execute steps or cycles or whatever you want to call them for executing instructions. Some instructions only use 1, some instructions use 2, and a couple of the instructions use 3. All right? And, for example, if you have an AND instruction, there it is sending out the memory address to the Raspberry Pi, again through the ALU, and telling Raspberry Pi, okay, I want to read this memory location. And then the Raspberry Pi responds back with, oh, here's your data. And it gets ANDed through the ALU circuit and then tossed back in the accumulator. So that's basically how that works. I'm not going to pound through all these other instructions, but that's basically how the state machine works, okay? So the state machine is just a bunch of flip-flops. There's one flip-flop for each of these states. Fetch 1, fetch 2, defer 1, 2, 3, and exec 1, 2, and 3. All right? And there's also there's an interrupt acknowledge. That's a separate state. So this thing, it does interrupts. Someone was asking. There's one flip-flop for each of these, and there's a little blinking light on the panel that I'll show you a little later for each of these states so you can tell what state it's in. All right? So there's, of course, my outline quit. All right, so that's the state table. Now the boards. Okay, so this little block diagram here, go back up to that, or down to it. So each one of these little things is a board, okay? Like there's an ALU board, and there's accumulator board, accumulator and link board, and an MA, memory address, program counter, and a board that holds the Raspberry Pi, and it also has the LEDs on it. Okay, so that the front panel board is combined with that Raspberry Pi thing. Okay, so there's one circuit board for each of these. Now, one thing I tried doing is doing it like bit slice style, where I would say, okay, each board is going to have 2 bits of everything on it. And I tried to get that to work out, and I just couldn't get it to fit well. So I ended up doing it this way, where I have a board with the ALU on it, a board with all these other things. Oh yeah, and stuck off the side is a board that has the sequencer and the instruction register. And the sequencer is what I call the state machine, or whatever you want to call that. All right, so that has all the state flip-flops, the fetch 1 and defer 2 and exec flip-flops on it, as well as the 3 bits of the instruction register. All right, so those are the boards, and I will show you little pictures of the boards. This is as I built them, actually. I made this sort of like log of building it. Okay, so here is like the sequencer board. So I started with the sequencer board because, well, that's the most interesting and most important part, from my perspective anyway, of a CPU, right? Is the thing that's going to control the state, saying, okay, what are we doing now, and what is the sequence of things that you're supposed to do to get a certain instruction accomplished. So this is the thing that has the little flip-flops on it that will step through each of the states, depending on what's coming from the instruction register and all that sort of stuff. And it generates all the control signals saying, okay, load the accumulator at the end of this cycle, or load the memory address register at the end of this cycle, increment the program counter, and all that great stuff. And I figured, too, if I can't get this board to work, there's no sense in spending money on the rest of it. So that's why I did this board first, because it's probably, the most complicated board of them all, because the memory address register is just, a 12-bit register, and the program counter, it's a 12-bit register with a little incrementer circuit on it, And similar with the accumulator is a 12-bit register with a little shift multiplexer on the input. So but the sequencer is, a bunch of flip-flops with, random wiring between them and stuff like that. And so I figured, well, okay, I'll do that one first, because if I can't get that to work, I'm not going to waste money on the rest of it. Anyway, so there it is. And you can see it's got 80 tubes in it. And the way the boards are made As you can, oh, great. No, I don't want to do whatever you idiot, stupid. I won't see that on a PDP-8, will I? No, I don't want you to make changes to my computer in the middle of a talk. It's just like Windows. You're about to give a talk, and then it says update, and it clears your screen, and you have to sit there and wait 45 minutes for it to update. Anyway, okay. So there's where the tubes stick out the back, and on the front, you call it the front. Okay, so the way the gates are, and I'll go over that. I suppose I should have. I'll do that next. Is the crystal rectifiers. Of course, when you talk about tubes, you can't call them diodes. You have to call them crystal rectifiers. Okay, so there's the crystal rectifiers, and here. I hope I have it. So here's a little chunk of one of the boards with the diodes on one side, and then you plug the tubes in the other side. So I have the tubes on these little boards here. Because when I started this out, I thought, okay, well, it'd be kind of wasteful to try to put the tubes and the diodes all on one side here. So I tried to figure out, well, how can I overlap them? And so I came up with this little crazy design here that you can plug this in like this, and they sort of overlap. Yep, let me hold it up. So here you have your diodes here, right? And then the two boards plug in here with their resistors, and I'll go over what these resistors are for and all that stuff. And then here, of course, is the edge connector, just these little 1/10-inch center pins, and they plug into the back plane. All right, so that's basically what that's trying to show there in 3 dimensions. Here you can see it. So that's how it's put together. Now, another advantage to this, too, and I thought, because I didn't know what I was going to end up using for vacuum tubes when I did this, right? So I could have one board, with these 6 J6s that I ended up using, and maybe one board that made out of 12 AX7s or some crazy thing like that, but they would still all fit to these, okay? I can even theoretically, take some JFETs and make one of these boards out of JFETs if I wanted to. Worst comes to worst, you could, make one of these out of JFETs if you couldn't come up with the vacuum tubes for it. So this design has sort of that modularity component built into it that makes it a little easier to work with, and then you're not really stuck with using a particular tube for the whole thing, actually. So that's how that's put together. That's what I'm trying to show here. But anyway, the sequencer board has, 10 of these 8-tube boards in it put together to make all the flip-flops. So, there's, 10 flip-flops or something like that on there. Well, yeah, 10 flip-flops for the state, and then 4 flip-flops for the instruction register. So, that's probably over half the tubes. And then, of course, there are all the ad hoc, and ors, gates, and all stuff like that come up with the what the state should be based on what the inputs it's getting from. All right? All right. So that's so I did that, like I said, I did that board first because I figured, if I can't get that one to work, it's not worth doing anything else, okay? And then the next board I did was the memory address register. Oh yeah, so I told you I was going to talk about the front panel. So there's the front panel board. Now the front panel board, I kind of cheated and used transistors for that because to drive LEDs from a tube would be kind of difficult, and I'd have all these tubes hanging out on the front panel. So I have transistors that interface the Raspberry Pi. There's the Raspberry Pi and little GPIO connector. Oh, I could use a little cursor, can't I? Yeah, so there's the GPIO connector, so that's its I/O bus, right? And then here are like all the LEDs, for the various cycles. Well, the instruction register is kind of washed out by the camera, but there's like the 2 LEDs for fetch and defer, execute, and interrupt acknowledge. This thing's tipped over on its side. You haven't figured that out yet. There's the program counter LEDs, and memory address and accumulator. go up, from there. So that's the front panel of the thing. And there's more pictures of the front panel later, too. All right. And down here, let's see. So there's a picture of that 8-tube board with no tubes on it. And there's a picture of it pulled off the back of the sequencer board. So you can see how it kind of fit together. So here's kind of the schematics if you guys are interested in it. Each of the vacuum tubes has 2 triodes in it, okay? So yes, it's an integrated circuit. Oh, well, you get two cells in one envelope. Okay, but anyway, so this is basically how the circuit works, the electrics of it. So you have the input voltage can be, anything over 3 volts is a 1, and anything less than a half volt is a 0. Okay, and that's because if you look at the data sheet for the 6J6, okay, well, in general, on a tube, if you have the grid at the same voltage as the cathode, okay, it's going to conduct, okay? And I have a little 3-volt Zener connected up to the cathodes. So that puts the cathode at 3 volts. So if the input is, 3 volts or higher, that's going to saturate the tube, right? And it's going to conduct as strongly as it can. And if you look at the data sheet for a 6J6, anything less than 2.5 volts, if the gate is or the grid is 2.5 volts below the cathode, it's going to shut the tube off, and it's not going to conduct. Okay, so it works like a JFET if you like, and then the output of the plate goes to a voltage divider, and the top of the voltage divider is at 120 volts, and the bottom of the voltage divider is at minus 96. So you work through the arithmetic on it, and you'll see that when the tube is not conducting, the output of that voltage divider should be, 4 volts or 5 volts, something like that. So yes, it works out to be, 5 volt TTL levels, coincidentally, right? Gee, I wonder why I thought of that. Anyway, so it comes out to be 5 volts. And when the tube is conducting, of course, it's going to pull, the junction of R1 and R2 down, which is going to lower the output voltage below 0 volts, okay? If the thing is not loaded, that 0 volts is way negative. It's be like minus 10 or minus 20. But when you load it with the inputs, it pulls it up near 0 volts. If you have it was designed for a fan out of 10. So if you, actually load it up with 10, they will pull it up to 0 volts. But anyway, it works out. So, and calculating the resistors is just a matter of, doing a little linear algebra, simultaneous equations, With the tube is shut off, you want 5 volts. When the tube's turned on, you want 0 or less. So that's the basic inverter. And then down there near the bottom is, using its diode DVL, right? Diode valve logic. So all the making an and/or invert gate, is typical stuff. So yeah, I have a 47K pull-up resistor. And this stuff here is on the, the big circuit boards here. All the resistor stuff is done on those little eight tube boards. Okay, but all this stuff down here below is what's on those big the big diode boards. Okay, and there's a little and/or invert gate, 2 inputs, and I think the bottom one got chopped off. 3 inputs there, so you can make an and/or invert gate out of 1 tube, using as many diodes. And I can't remember what my widest are, but like there's a rotator circuit that's got, I think, like 5 inputs, two AND sections and 4 or 5 OR sections to it. So these can go pretty wide, and I didn't have any problem with them. Down here is how I make a D flip-flop, which is, most of my flip-flops in this thing are D flip-flops. And this circuit is from the 74 data sheet, using 6 triodes, right? Now, someone suggested, well, you should use pulse latches because here's what they did in the PDP-8 to save a few transistors is they used pulse latches. And I had already kind of done my design, and I thought about pulse latches way back when, when I started doing this, and I thought, well, I know these 6 gate flip-flops work. I'll show you why, because I'd used them before, and they're foolproof, and my tube count was low enough that I thought, well, I've kind of gone far along this path, and so there's no real reason for me to do any different. These are tried and true, whereas pulse latches, well, you'd have to get the pulse width just right, and you'd have to have the rise time going into the things just right to get the capacitors to, time the pulses right, and it just wasn't worth the effort. So I kind of stuck with these, these are sort of level. You could ramp up, turn a potentiometer up, theoretically over a few days, and these things would trigger right. Okay. And, I wrote out a little explanation of how they work, but there it is. And I'm not going to pound through that, bore everyone to death with that. Unless you ask me later. All right, so let's see. Those are that stuff. Okay, so more stuff. Let's see, there was a sequencer board I talked about. There's all the gates. The state table we talked about. In case you're interested, here are the signals that go to the Raspberry Pi. Okay, the Raspberry Pi generates the clock signal, right? So it's going to say, here's the beginning of the clock cycle, and then there's just a little simple software timing loop inside the Raspberry Pi. Well, it's reading the Raspberry Pi's timing register, and then it knows when so many cycles have proceeded, and it knows to drop the clock. And the reason why I had the Raspberry Pi generate the clock cycle is in case Linux decides wants to take a coffee break and, go do something else, like shuffle some, non-volatile RAM blocks around like that, do some wear leveling, It's not going to miss a clock pulse generated by, if I had the tubes generating the clock. So that's why I had the Raspberry Pi generate the clock cycles. And plus, then it makes it easy to program. I can just, in software say, okay, try, so many kilohertz of cycling. Stuff like that. The DINA is the data enable, and it enables the signals to go from the accumulator and gates them into the Raspberry Pi GPIO pins. There weren't enough pins on the Raspberry Pi connector to go both ways on the data bus, so the data bus is bidirectional. Okay, so I have to have a gate signal to say gate the tubes onto the Raspberry Pi, and then there's another one that says, okay, now the signals are going back out. QENA, oh yeah, that's listed down a couple steps below. Another thing that the Raspberry Pi outputs is when you do an I/O instruction, part of the I/O instruction can say, okay, skip the next instruction if the teletype is ready to accept a new character for printing, or if there's a keyboard character. So at the end of an I/O instruction, the Raspberry Pi has to be able to tell the tubes, okay, we want you to skip an instruction. So that's what that signal is for. IRQ is the Raspberry Pi telling the processor, okay, I'm requesting an interrupt. So at the beginning of the next instruction, you're not going to do the instruction, you're going to do the interrupt acknowledge cycles instead. The KINA signal is, again, the Raspberry Pi is outputting data to the tubes, like here's the contents of memory that you requested to read, something like that. Reset is reset. That puts the state machine back at the fetch cycle with the program counter 0. And then here's the rest of these guys, I don't know, like read and write down there at the bottom, or the tubes telling the Raspberry Pi, okay, I want you to read memory, or I want you to write memory, that sort of thing. All right? Again, if you have questions about those states, or pins. But anyway, you can ask later. But those are the I/O pins that go to the Raspberry Pi. Those are the GPIO pins. So you could theoretically take the Raspberry Pi off, and you could make, a stupid memory card that just responds to read and write, okay, and it would do read and write, okay. Or you can make I/O devices that respond to, where it says I/O instruction and actually do that, a stupid card to, write a serial port or something like that. So I tried to keep it where, yeah, theoretically you could do that. Okay, you could make stupid I/O devices plug on that Raspberry Pi. I didn't want to put any intelligence in the Raspberry Pi beyond it doing a simple read or write, to memory, or it doing, what a UART board, a simple UART board would do to read or write a serial port. Okay. There's a big asterisk on that now, because the Raspberry Pi knows what is being transferred, in and out of memory every cycle, or for every I/O instruction. It has a subroutine in it where it says, this is what the tubes should be doing this cycle, and it verifies that the thing actually does that this cycle. So it knows whether or not the tubes are screwing up, and it'll print an error message, and here's what the last, 16 cycles did. And so I've been very experienced with that happening, of course. If I turn this, I can turn the speed up, and eventually, it'll start barfing out, like the top bits of the adder will start being wrong, okay? Because, as it goes through the carry circuits, the top bit will not make it in time back around. I was talking about the synchronous clocking. Well, if the top bit, soaks through all those tubes, and it doesn't quite make it, and you clock the accumulator too quickly, it will, come up with the wrong answer. And the Raspberry Pi will know about it right away and say, this is the wrong thing. All right, let's see what else I skipped over. ALU board, okay. So anyway, there's all that stuff I talked about. Oh yeah, here's a list of all the backplane signals. Now I'm not going to pound through all of those. But the backplane is not the haphazard wire, random wiring that you find in a PDP-8, because I wasn't going to put up with any of that. It's just, straight buses. Every board has access to the signals, and I think there are, 122 of them I ended up with. So every board has 4 32-pin connectors on it. Each one has pin 1 as ground, and the rest are signals. And so these are divided up on those pins. And then there are 3 6-pin power connectors on each board. All right. And then there it is, standing upright, yay. There's some power, there's a 120-volt power supply. And let's see, was it 0.43 amps there? And I think is that just for that one board? Yeah, that's just for the one board. And there's the other power supplies, I think. That's the minus 96 there on the right. And that power supply down there on the left. Okay, so each one of these boards has 8 tubes on it, and there are 6 J6s, so each tube is 6 volts. So 8 of them, the filaments are in series, so that gets 48 volts for the tubes on one of these boards, okay? I'm not doing them in parallel. That would be way too many amps, right, to deal with. So that power supply there on the left is a 48-volt power supply. And these power supplies, they have a little control input that you can ramp. You can control the output voltage with an input voltage, and it's basically just a big power amplifier in a way. You put, 1 volt in, you get 10 volts out or whatever. So, or proportional output. And so I just have a big capacitor. You can see that I made a little I should have brought one of those little piggyback circuit boards. But it's just a capacitor and a resistor and a couple of diodes. And when you turn the thing on, it ramps the filament voltage up over 30 seconds. So I don't get a when you turn the thing on, where it has all the cold filaments. So it slowly brings the filaments up over like 30 seconds or so. So that's how the filament supplies work. All right, so here the next thing I made was the memory address register board. And that's basically just a simple 12-bit register, okay? It doesn't have any smarts into it. And so I did that second so that I would have something that I could cycle data into and out of and have the sequencer board clock through it, right? And so I tested that and got that to work. And let me show. And then next I made the ALU board, which does adds and ands and complements, things like that. And I think you can do an increment. And that went, I put that together. and plugged it in, and it worked for like 10 minutes or so, and then it started going little cuckoos, okay, and started getting all these crazy results. Now, so what I did is I made these little paddle boards, and these plug into the edge connectors. Well, let's see if I can plug it into the edge connector. Thusly. Oh, these are power connectors here. But these are the signal connectors, and on a full board, this one's cut up, but there are 4 of these. Okay, and these have a USB connector here, and this is a little parallel I/O thing connected up to USB. It's called an I/O Warrior, and it basically can generate 32 signals going in and out, well, 31, but it can generate the signals going out and read back. So I can basically plug 4 of these into a board and unit test the board and have the Raspberry Pi pound the, bejesus out of the board. And I have a test program that runs on the Raspberry Pi that just generates random number sequences into the board. And since it knows how the board works, it knows how the board should respond, right? So if I want to test a board, I can unplug it from the backplane, plug these paddles into it, and let the Raspberry Pi, beat it to death. Okay, and fine. And I found things like, I had a diode in backwards, and I found one of those using this. And I had a flip-flop that was stuck on a bit, and I ended up swapping the tube, and it was fine after that. And I didn't really have too many problems other than that. But these paddles, were definitely a big help testing things out. And I had to go through, I think 2 generations of these paddles to get the paddles to work right. Anyway. All right. Let's see, paddles. Oh, and these paddles will also plug into the back plane, okay, because they're just the signals. So I can plug these paddles into the back plane, and it's with all the boards plugged into the back plane or just a certain number of boards. And the Raspberry Pi, again, knows what the processor is doing every cycle. And so it can check at the end of the cycle by reading out the paddles to say, oh, yes, okay, these signals are what should be there, okay? Or, oh, these signals are not, what should not be there, okay? Also, if I have missing boards, like if I don't have the program counter board, which was the last board I did, these paddles, the Raspberry Pi can say, okay, well, he's missing the paddle boards. Here's what the program counter should be doing this cycle, so it can drive the program counter signals out to the Raspberry Pi, or out to the bus from the Raspberry Pi, and fill in the missing signals and have it chug along. So theoretically, yeah, you could unplug all the tube boards and it could run all just off the paddles, but that's kind of silly. Anyway, that's what the paddles do. And so here I have them testing the ALU board. I think that's on the left, yeah. And so the ALU board is just combinational logic. There aren't any flip-flops on that. That's just doing add and and complement and stuff like that. So the Raspberry Pi is just using the paddles to just dump random number sequences out to the board and then verifies them at the end of each cycle to make sure that if it's randomly told it to do an add, that it's actually done an add, or whatever logic function. So it just dumps them out to the board and then reads the values back to make sure they're correct. Okay. So that's what's going on. That's what the paddles do. Now, one little interesting little story is, okay, so I was wondering, I can't remember exactly what triggered it, but at some point I measured the voltage on the cathode and I went, wait a minute, this is 3.6 volts. Why are my cathodes at 3.6? They should be at 3.0. And so I measured, right across the Zener diode, 3.6. Am I overcurrenting the Zener? No, it seems nice and cool. And, here's the 220 ohms going to 5 volts, and that should be, only 100 milliwatts or something like that across the Zener. So it shouldn't have any problem with it, a half-watt Zener. And so I got a Zener out of the bag with all the others. No, 3.6 volts. They're supposed to be 3.0 volts. I ordered them from a certain digitally keyed supplier, but we stuck them under a microscope, and they said, yeah, 3V0 or whatever the code was on them. So they were all stamped to be 3.0 volt Zeners, but they were 3.6. And I wrote our digitally keyed supplier and said, you know, I got a bunch of 3.6 volt Zeners. They're great for 3.6 volts, but I ordered 3.0 volts. And I never heard, they refunded my $3.61 or whatever after I put them in all these boards. Anyway, I never found out what they did, but obviously, you know, the problem was with the manufacturer, not with the supplier, because they were all stamped to be 3.0 volts. So I ordered them from some mousy place down in Texas, some replacements, from a different manufacturer, from VCF. These were Nexperian or something, I can't remember. Yeah, these were NXPs, and so I ordered some from VCF. But I don't know, the 3.6 volts didn't seem to be an issue. I thought, you know, it would be critical because I had that, you know, the cathode was at 3 volts, and, you know, anything over that is supposed to be a 1. And, you know, then I had to go down, you know, 2.5 volts below that. And if I have to go down now to, you know, well, if everything's a little higher voltage, it's going to be messed up. So, but it wasn't. I thought it would be more voltage sensitive than what it was, but it turned out, well, it doesn't make so much of a difference. So on any boards going forward, I use 3.3s on them, and that seemed to work fine. So anyway, so that's a little weird thing. I didn't think that would be possible and have the freaking diodes on the wrong voltage, but who knows. Anyway, okay. So next, let's see. Get my outline going here. Stupid thing keeps timing out. Oh, I'm running out of time, aren't I? Anyway, there's not a whole lot. Well, there is one little thing about this. Okay, so let me get my other page going because I'm going to kind of blitz through the rest of this. So let's see, design. Oh, this is old. Okay, let me get this. Oh, great. All right, well. Oh, I can't type in the wrong name. Okay, so there really aren't any schematics as such for this, okay? It's all written in the Verilog. It's sort of a Verilog-like language, okay? I didn't make schematics. Like, let me open up. That doesn't work. Ugh. Oh, there it goes. So, yeah, there. So I wrote it in the Verilog language, sort of like here's the rotating circuit, okay? So the rotating circuit output, you know, is this Boolean equation, a bunch of gobbledygook, right? Okay, and then I have a big Java program that I call NetGen, generates the net list, right? So it reads in all this Verilog-like code for each board. Okay, there's one of these Verilog files for each board. It reads this in, and then it generates those little and or invert gates and plops them on the circuit board. Okay, so I don't really have schematics as such, and because if I want to change one of these and, you know, have it change the gates, well, I don't want to have to sit there and erase a diagram and do all this crazy stuff to draw stuff around. So I did it this way, and there really isn't a schematic. And so how can you possibly debug something when it goes wrong? Well, it's not really that hard. You don't really have to trace circuits around, okay? So let's say I'm trying to debug a stuck flip-flop, right? Like the fetch 2 flip-flop is always stuck on or whatever, right? So you might want to say, well, where are the tubes for that? So I have my little program, my Java program, output this report file that says, okay, well, here's where the tubes are for the fetch 2 flip-flop. So if the fetch 2 flip-flop gets stuck, you can find the tubes at, you know, 6.9 inches over from the from the left edge of the board and 5.6 inches down, okay? And so there are the little gates for it, and you can go there and measure the voltages. So you really don't need a schematic as such, at least, I don't think you do anyway. Here is like a gate, okay? So a gate equals some Boolean equation, okay? And then the report program will tell me, okay, well, the output of that equation is at that position there, and here are all the diodes going into it and all that stuff, so you can figure out from that what diode has gone wrong. And like, here's the little printed circuit board, and that one thing said J17, I think, and there's J17. And then there are all the diodes going into it. So you can measure the voltages on the gates and figure out which gate or diode has gone wrong. And there's the plate is on the top, and there's the grid going into the tube there on the bottom. And these middle pins, you kind of have to watch out for these. Some of them are ground, and some of them are the high voltage, and some of them are the filaments. So you have to make sure you don't slip a probe on there. You might get a little bang out of that if you did. But other than that, it works out. And, you can measure the voltages that go to the grid by measuring, these diodes. So that's basically how it works, how that part of it works that we've seen before. Software, here's a little test program that exercises the boards. You can plug the paddles into the back plane. And this one here, the back plane is missing the program counter. So the paddles are making up the program counter, but it's checking the output of the tubes every cycle for the stuff that's in red. And down there on the bottom is the GPIO connector. Some of the stuff is coming from the tubes, and some of the stuff is coming from the pi for that. But that's basically it. I hope that gave you some idea of what I did to make this thing actually work. And again, it's just the processor. I wasn't trying to do, memory or, that they would have done back in the day, because I really have no idea how I could possibly do anything like drum memory or mercury delay lines or anything like that. So I just, restricted myself to doing the processor to keep it sort of a constrained project. All right, so I guess that's pretty much it. That's all I really have time for. If there are any questions, of course, yeah? Maybe we don't. Stand up and yell. Come here to the front and use the mic here. You're welcome to.
Two quick questions for you. One is, did you look at any two-computer schematics for inspiration, or did you do this?
Not really. I just sort of did it with thinking. One thing I didn't talk about was there's the Hode computer, and I did that the year before, or the couple of years before. And this is a transistor computer, and this was a design all my own. It's a 16-bit transistor computer, and you can tell the designs are practically the same. The and/or inverts and the flip-flops are all the same, and it just uses a tube instead of the transistor. So it didn't really change all that much. Okay, number two.
The second question is, what do you estimate the marginal cost to build the next one is?
Oh, well, I probably someone said they were going to buy me a big box of big box of relays, and I'm not thinking of building another tube one yet. Haven't thought of one. Yeah.
So, did you think of doing a digital front panel using mixing tubes?
What's that?
Could you do a digital front panel for it using Nixie tubes?
Okay, well, interesting. Okay, so at the bottom of this, let's see if I can find it quickly. As you will notice, nothing comes up. Oh, yeah. Let's see, at the very bottom of this is a picture of the thing done. I didn't show. I suppose I should show you this. Okay, so here's a picture of the thing done. Well, let me get the big picture of it. You'll notice on here, there's this case, so this is a little... No, maybe it's not. Maybe it isn't. Well, so much for that. Well, all right. Anyway, so there on the front panel of the thing finished. Good Lord. there's a frequency counter, okay, and it's got a 7-segment LED. Well, I just got in the mail last week the stuff I need to make a Nixie version of it. So it's going to have Nixie. If I want to actually take it apart and put that in, but this bloody thing. Anyway, all right, so that's the deal with the Nixies. Oh, there it is. Okay, now let's see what happens when I try. Get a little better picture of it. Oh, come on.
I think it messed up objective. High res.
Yeah, it must really freak it out somehow. Okay, but anyway, well, you can kind of see here. Right, a little trophy shop etch on a board that says PDP-8 there, right? And anyway, there's a frequency counter. So I have Nixies for that. So I'm gonna replace that with Nixies at some point.
Did you say about the frequency that it runs at, where it kind of craps out?
Yeah, around 25K.
Okay.
Yeah.
And you're matching the instruction set, right?
Yeah,
And the code you write in the Raspberry Pi, it's in assembler for this, right?
yeah. So it'll run OS 8, and it'll run EduSystem 20 basic. We had it going with 2 teletypes or 2, well, terminal screens. I shouldn't say teletypes as such.
And the logic level inside the ALU and everything, is that trying to match the gates and flip-flops and everything original, or just mainly the instruction set?
It doesn't really have anything to do with the original design as such. It's not gate level
Right. Okay.
copy of any of the designs. No,
Thank
it
you.
just matches the instructions, yeah.
Can you terrify us with the power consumption when it's running?
Yeah, 1.7 kilowatts. Power factor 0.97, if you want to know. Yeah. Yeah.
And only 3 voltages.
Yep, it has the plus 120. Well, actually, originally I designed it to be plus 120, minus 96, and plus 5. Okay, and then I fooled around, and it would run 18 kilohertz like that. And then I fooled around with the voltages, and I got it to go up to 25K by going down to 118 and bringing the minus 6 up to, I guess you would say, 87. So I got a little more speed out of it by playing around with the voltages. So, yeah, I got 2 people in the back.
Questions in the back? Yeah, I'll
Yeah.
come back there.
I guess we're running over into lunch. Well, not yet. Uh-oh, I'm going to get some heavy ones now.
One of the problems that I often ran into was when I was building a flip-flop, if I had a lazy tube in the middle, maybe it was weak on emission or something like that, I would get really erratic behavior out of the flip-flop. Sometimes it would behave, sometimes it wouldn't. Is that something that you ran into a lot with the 6J6s that you used, or did you get new old stock?
Okay, I had 2 flip-flops that were a little flaky, right? And what made it worse is the scope. I had a modern, scope, and I put it on there, and it would behave a little bit differently with the scope. So, I would narrow it down to that flip-flop, and then it's just a matter of switching tubes until I got it to work. And, I've had 2 tubes out of the 320 some that were, flaky. So I hadn't done any real testing on them beyond that. I said, all right, it works. Let's get the board in there and get it going. But
Were all of your 6J6s poles from like radios and TV and stuff like used tubes, or did you manage to find new old stock stuff
okay,
somewhere?
well, all right. I'll go through my little tube story with you. So let's see, on my hacks or a day IO page, do I have that up here? So I made a little hack a day IO page. Now there it is. So anyway, they had some information too about, oh jeez. All right, well, anyway, okay, so pretend you're seeing a hack a day IO. Okay, so here's the deal with the tubes. I told this story yesterday. I'll tell it again. So every month or so at MIT, they have one of the parking garages, and they have the MIT flea market. Third Sunday of every month, is it, Bill? I think, yeah, third Sunday. So you go down there and you look around. Here's this guy, and they bring their, ham radio stuff and anywhere from the ham radio, old ham radio gear through to cheap laptop, laptop something or other you want to call it. And so here's a guy with a big spread of tubes out on the table. And I was looking around and I saw this little box of 5 6J6s. Huh? So I got off the phone and looked up what are 6J6s. Oh, dual trios. Oh, I could use those, but those would probably work out pretty good. So I gave him the $10 he wanted. He wanted $2 a tube, so $10 for that box of 5. And I took them home and stuffed them in a perf board and experimented and say, okay, yeah, these resistors work for the gates and all that kind of stuff. And then, so I ordered some circuit boards. So I could put together little flip-flops, these are, or little gates, you know, little and or invert gates here with the resistors and stuff like that. And so while I was waiting for these circuit boards to come, I looked and I thought, okay, now how common are 6J6s? Is that just a weird one-off find, or are there a lot of them around? So I looked on the web, of course, and I found a guy on eBay selling cartons of 200. If that showed up, it would show you a picture of it, but it's not. But I bought a carton of 200 of them for $150, and that was quite a deal. So I thought, yeah, that's probably one of these eBay too good to be true deals, but I sent $150, it was worth it. And I actually got a carton back, 200 tubes, and I pulled those tubes out and stuck them in this board. And I said, oh, yeah, it seems to work. Okay, and fortunately he had more of the cartons, so I bought 2 more cartons and ended up with 600 6J6s. So that's where the tubes came from. Now, I've looked on the web, and I see someone selling those same cartons for $400 now instead of the $150. So I don't know how much longer they're going to last, but that's how I ended up with 6J6s, and it was quite a coincidence as far as I'm concerned, freaky, you know, because here's this guy at MIT, and I just happened to see the 6J6s. They were standing out at me, leaping in my face, you know, practically, saying, oh, go find more of me on eBay or whatever. What's that? Anyway, so, but like I said, the design was set up where you could use different tubes, you know. So if you had, you know, some 12AX7s, you could make one of those little 8-tube boards for 12AX7s, and if you had some 6J6s, you could, you know, make one of the boards up for that, and you could mix and match, theoretically. So I was thinking, well, maybe I'll end up doing that, but no, I was fortunate to find just a big batch of 6J6s. And someone was telling me yesterday, oh yeah, well those aren't used for audio, so they might be more common than, because the audio people aren't scarfing them up. Yeah.
Have you thought about using Williams tubes for the storage, so that you'd be using
Use what?
Williams tubes. So Williams tubes are 2D addressable. They're essentially CRTs.
Okay.
That
I mean, are they available and affordable? Because I'm not going to spend money on
they
stuff.
They were a sort of failed experiment before core memory.
Yeah.
And I'm not sure how available they were even then. Right, you might be able to, homebrew a Williams tube. It's conceivable, yeah. I don't know, but how many people have tried to build a vacuum tube computer in the last 4 years?
Yeah, and again, you know, the scope of the project was just the processor, and you know, I just wanted to do the processor and not bother with memory stuff.
One other quick question.
But yeah, it
how
might
reliable?
be a good extension. Yeah.
How reliable were the tubes? How did you find them to be?
Oh, this thing will run for hours. Yeah,
Nice.
It'll just crank away. I can run random instructions tests on it for hours. You know, I can boot, you know, OS 8 and run Edgy System 20 basic on it, and it'll do, you know, it'll just run for hours, sure. Yeah. Yeah. Again, you know, if I tweak it up to 26 kilohertz, it won't. It'll crap out, you know, maybe in 5 minutes, or, you know, maybe might in 30 seconds, depending on what, you know. Exactly. What's that?
You don't see tubes burning out.
No, I think tubes, they have tube life of, you know, a few thousand hours right on a tube. So, you know, and I've run the thing, I think, a whole of, you know, 30 or 40 hours total. So I don't know if I'll ever get to, you know, 200 hours by the time I kick the bucket. So I'm not too worried about tubes burning out. I have, you know, 500, or, yeah, I have like 300 spares, so. Yeah, well, I imagine when they start going, they might start all going at once, and, you know, well, that'll be the end of it. Too bad. You know, I'm not going to beat my brains out over it. Yeah, so I think that's it. Oh, here's another one of my passions, if people like flying saucer stuff. I don't know if any of you know what C-SETI is, but I'm a big C-SETI fan and all that kind of stuff. Anyway, Oh, a certificated flight instructor, too. That's another one of my occupations, but certificated. All right? So I guess that's it. And thanks a lot for the questions. Thanks for coming.